In this video lesson, we're going to talk about forces and introduce the idea of forces and talk about what types of forces and general forces that there are. To begin with, we need to have an understanding of what Newton's first law says. Newton's first law states that an object at rest will remain at rest, and an object moving will continue to move in a straight line and at a constant speed if and only if the net force acting on the object is zero. Now that sounds like a lot, but let's break that down into something that we can actually make sense of. First of all, an object at rest will remain at rest. This seems to make sense. For example, if you had a box sitting on a tabletop like so, you would expect that box to remain at rest unless something came along, such as a hand or another object, and made it move. So that makes sense. The second part states that an object moving is going to continue to move in a straight line, meaning its direction will not change, and at a constant speed, so it won't speed up or slow down, if and only if the net force acting on the object is zero. Now, the key thing we're going to find in this unit is that it's not force, but it's net force, meaning you can have forces acting on an object and it still is going at a constant speed. The main idea that we need to understand and absorb in this slide is that objects want to keep doing what they're already doing. If an object is at rest, it wants to stay at rest. And if an object is moving in a straight line and moving at a constant speed, it wants to keep doing that. It doesn't want to speed up, it doesn't want to slow down, and it doesn't want to change direction. The only thing that is going to change an object's motion, whether that's speed or direction, is an unbalanced force. So that's what we're going to see in this unit. This is also called the law of inertia. And the reason why it's also called the law of inertia is because inertia is defined as an object's resistance to motion. So if an object has more inertia, it's harder to change its motion. So that makes sense why it's called the law of inertia. Now, since this unit is on forces, let's take a moment and talk about what a force is and what they can be classified into. First of all, a force can be defined as a push or a pull. Notice that the unit, or not the unit, but the variable or symbol for force is F. Now, what do we measure forces in? Forces are measured in units called newtons, which is the capital N. So the symbol for force is F, but the the unit for force is newtons. Just like the symbol for velocity is V, but the unit for velocity is meters per second. Or the symbol for acceleration is A, but the units for acceleration is meters per second squared. The symbol for force is F, and the unit is newtons. Now, if you were to take all the entire forces in the entire universe and classify them into two main types of forces, that would be contact forces and field forces. A contact force is just that. It's a force that comes from contact or touching. So it's defined as when an external object touches the system, which is the stuff you care about, and exerts a force. So for example, if I pick up a book, if I push a wall, if I pull on a rope, all of those are forces that involve touching or contact. The other type of forces that you're going to find are something called field forces. These are also called at a distance forces, and that's spelled at a distance. And the reason why they're called this is because these are forces that are pushing or pulling an object without coming into contact. So a classic example is gravity. If a person is skydiving in the air, the person is not touching the earth. However, the person does feel pulled towards the earth's surface, and that's because of a gravitational field. Other field forces would include a magnetic field, such as if you take a magnet and make metal move without touching it. And finally, an electric field. It's not written on here, but an electric field is another field force. For example, if you've ever taken a sweater out of the laundry, you may have experienced your hair being drawn to the sweater. The hair is not touching the sweater, however, the hair does feel attracted or pulled towards the sweater based off of an electric field. Now, these are two main categories of forces, but what we're going to see is that there are sub-forces or specific forces that fall under these two categories. Before we look at those forces, we need to understand a concept known as equilibrium. In fact, Unit 4 is all about forces that are in equilibrium. When the sum of the forces, and this Greek symbol right here stands for sigma, that means sum. When the sum of the forces, or total of the forces, are equal to 0, then the object is in a state of equilibrium. And what that means is the object's motion or velocity is not changing. So what does that look like? An object's velocity that's constant or not changing can mean two things. It can either mean the object is at rest, or it can mean the object is going at a constant velocity. So there's no acceleration. Keep this in mind. The sum of the forces are equal to 0 when an object is in equilibrium. So if an object is at rest, or if it's moving at a constant velocity, the object is in equilibrium. Alright, let's go ahead and look at some of the different types of forces that you'll see in this unit. Notice this table here. The first column is the name of the force. We're going to look at friction, normal force, spring force, tension force, and then a force called weight. Notice the second column has the symbols. Friction is F sub F. Force normal can be F sub N or just capital N. Spring force is F sub S. A tension force is F sub T or just a capital T. And then weight is either F sub G or capital W. Now what are they? What is their definition? Well, first of all, friction is a force that opposes sliding motion. It can also be classified as air resistance. So an example of friction is if you push a book across a table, the table is exerting a frictional force on the book. The book is sliding, let's say, to the right, but the frictional force will want to oppose that and will go to the left. That's why it says under the direction that the direction of friction is always parallel to the surface and in the opposite direction. Now, normal force is something that's a little different that we may not have ever thought of before. A normal force is defined as a force that's exerted by a surface on an object. A surface can mean many things. It can mean a table. It can mean a wall. It can be the ground. It can be a chair. Any surface that is constant and stable, that's not moving. Now, what is the direction of the normal force? The direction of a normal force is always perpendicular and away from the surface. So let's take some examples. If the surface was a tabletop like so, the force normal would be perpendicular and away, like that. If the surface was a wall, like this, the normal force is perpendicular away from the wall. What if the surface was a ramp? Once again, the normal force would be perpendicular and away. So the normal force is always going to be facing perpendicular and away. It's the force that the surface exerts on the object. Now, let's look at the third one. The third one is a spring force. This is going to be a force that's applied while using a spring. Specifically, it's the force applied by the spring in order to restore itself back to its original shape. Now, what's the direction that the spring force will point? Notice this, the direction is opposite that the spring was deformed. So let's say you had a spring like so. This is a spring in equilibrium. Now, let's say I stretched the spring like so, and I attached a block to the end of it. Which direction would the spring force be pointing? Well, we deformed the spring this way, or down, so it would make sense that the spring wants to pull up. It wants to go back to its original restoration. What if instead of taking the spring and stretching it, I squished the spring in? So something like this. Okay? I pushed the spring in, so it makes sense that the spring would want to push back out or away. So the force of the spring is always going to be opposite the direction in which the spring was deformed. If it was stretched down, the force spring will pull up. If the spring was pushed in or up, it'll push back down or down. The fourth type of force is tension force. This is going to be a force specifically from a string, a rope, or a cable. The direction makes sense. It's always going to be facing away from the object and parallel to the string. So for example, let's say I had a block that was hanging from a ceiling by a string. So something like this. The string wants to keep the block up, so it would be pulling up like this. If I was taking a block and maybe I was pulling it because I had a rope, such as that, the force tension would be up and in that direction. So the force tension is always just going to face the same direction as the string itself. Oh, and I'm sorry, that should be down here for string. Whoops, it's messing up there. But you get the idea. Finally is weight. Now, weight is a very important one in this unit. We'll use weight all the time practically. Weight is another way of saying force gravity, and that's why it has the symbol F sub g. Now, the symbol for that is F of g or W, but the definition is gravitational attraction between objects. So anything that has a gravitational pull on it is going to experience force gravity. In other words, any object that's on the Earth is going to experience a gravitational pull or force gravity. This direction is always straight down towards the center of the Earth. No matter what the situation is, force gravity always pulls straight down. All right, let's go ahead and cover a couple of these forces in more depth. Let's start with force gravity. When we talk about force gravity, we need to make sure we understand the difference between mass and weight. Mass versus weight is this. Mass is a measure of amount. It's how much matter you actually have. And in physics, we measure mass in kilograms. So for example, you have a certain mass. There is a certain amount of matter that makes you up. You have organs, and you have thousands and billions of atoms. You have all this material that makes you up. That's not going to change unless, of course, you lose some material in some sort of way, which hopefully would not happen. Your mass, in other words, is constant because the amount of matter that makes you up is constant. Your weight, on the other hand, is a measure of gravity's pull on your mass. And that's what's known as a force. So when you step on a scale in the bathroom and you read your weight, what you're really measuring is you're measuring gravity's pull on your mass. So if you measured your weight in your bathroom versus maybe measured your weight on the top of Mount Everest, it would probably read slightly different because gravity's pull on Mount Everest is different than gravity's pull probably in your bathroom. Same thing, if you were to take the same bathroom scale and go to the moon and step on the scale, you would definitely read much different than on Earth because gravity's pull on the moon is different than gravity's pull here on Earth. So when we talk about force gravity, we're really talking about weight, not mass. Now there is a way that you can calculate the force due to gravity, and that is taking your mass in kilograms times the acceleration due to gravity. And remember, g is always 10 meters per second squared. Now notice, when you would take your mass times your acceleration of gravity to get your force, what do you think that breaks that up to? In other words, what is a newton? Because we know forces are measured in newtons, but notice what that breaks down into. A newton is just a kilogram times meter per second squared. Because if you take your mass times your acceleration, those are the two units that together make up a newton. That'll come in handy later on. We'll want to remember that a newton is equal to a kilogram times meter per second squared. Now in America, we don't usually measure ourselves in the bathroom scale using newtons, we use pounds. So it is useful to know what that conversion is. 1 pound is equal to 4.45 newtons. So remember that you'll always have more newtons than you have pounds. So let's look at a couple examples. If a person has a mass of 40 kilograms on Earth, what is his weight in newtons and what is his weight in pounds? His weight in newtons is very simple. Remember, force of gravity in newtons is equal to your mass times g. So that means that 40 kilograms times 10 meters per second squared is going to give us his force of gravity, which is 400 newtons. Now we just have to convert that into pounds. How much would that be? Well, remember, there's always more newtons than there are a pound. So you should have less pounds than newtons. I'm going to take my 400 newtons and I'm going to set up a conversion. I know that there are 4.45 newtons for every 1 pound. Notice my newtons cancels out now, and if I take 400 divided by 4.45, I'm going to end up getting my answer of approximately 89.9 pounds. Let's look at another example. If a hammer has a mass of 2.5 kilograms, how much does it weigh, A, on Earth, and B, on Mars? And Mars's G value is 3.3 meters per second squared, roughly about a third of what it is on Earth. Well, Earth, we're just going to take the mass, which is 2.5 kilograms, times the Earth's acceleration of gravity, which is 10 meters per second squared. This would come out to be 25 newtons. Notice it doesn't tell us specifically it wants us in pounds. So if ever it tells you how much does it weigh and doesn't specify, it's assuming newtons. So we can leave it just like that, 25 newtons. Now on Mars, the same mass of the hammer is going to be pulled down with an acceleration of 3.3 meters per second squared. And that's going to come out to be 8.25 newtons. So it wouldn't weigh as much on Mars as it does on Earth. Finally, let's do one more. A person weighs 145 pounds. What is the person's mass on Earth? In this case, we're having to work backwards. Notice it gives you a force, it's in pounds, of 145 pounds. It wants to know what is the mass on Earth. In order to even get to mass, we need to be in newtons first. So what we first have to do is take 145 pounds and convert that into newtons. We know what that conversion is. For every 1 pound, there is 4.45 newtons. Doing so cancels out the pounds, and when I multiply those two together, I end up getting, for my number of newtons, about 645.25. So now that that's my number of newtons, or force of gravity in newtons, I know that's equal to the mass times the acceleration of gravity, which is 10 meters per second squared. Divide those two, and I end up getting my mass is approximately 64.5, and since I solve for mass, that unit is in kilograms. Now let's go and take a look at force normal. Force normal, remember, is a force that is perpendicular to the surface. Now force normal does not have an equation. Instead, it's situational. So let's look at two situations. I've got a 3.5 kilogram block. The first one is resting on a horizontal surface. The second one is being pushed up against the wall, probably by a hand or something like that. So in the first one, let's take a look at the block. The block, we can see, has a force or a mass of 3.5 kilograms. So in other words, we can say the force of gravity that's pulling it down is 35 newtons. So I figured that out just like I did on the slides before, 3.5 times 10. Now that's the force that gravity is pulling down on the block. But notice the block is just sitting there on the surface. So it's in equilibrium, meaning it's at rest. And equilibrium means that the sum of the forces have to equal 0. So if I have a force of 35 newtons from gravity pulling down, the force normal that's facing directly up must be equal to that. And therefore, it's 35 newtons as well. It has to be 35 because the box is not moving, it's in equilibrium. And so the forces have to cancel out to be 0. Let's take a look at the second situation. The second situation still has a 3.5 kilogram block, and so it would still have a force of gravity of 35 newtons pulling it down. But notice in this example, the force normal is not acting vertically. The force normal is going to be from the wall pushing it out to the right. So in this case, the force normal is not going to be from gravity, but it's going to be from something that's holding it up. For example, let's say I was pushing the block against the wall with a force of 50 newtons. If I was pushing the block against the wall with a force of 50 newtons, this example, the force normal would have to be equal to 50. And it's because in this example, the force normal has to balance out the applied force, not the force gravity, because force gravity is vertical, while force normal in this example is horizontal. We'll do some more practice examples with force normal later on. The final force I want to talk about is frictional force, or F sub F. First of all, friction is defined as a force that opposes motion. So if an object is moving, it's going to oppose it. It also is going to be a force that opposes motion that wants to start. So you can see there's two types of forces here. There's static friction, and then there is kinetic or sliding friction. Static friction is a friction that needs to be overcome by another force in order for there to be motion. So in other words, static friction is the friction that's keeping an object from moving. So for example, suppose you had a ramp, and suppose you had a block that was sitting on the ramp, but the block was just staying there. I'm pretty sure you all have seen situations like this, where you have something on an angle that should be moving down the ramp, but it's not. It's just staying there. And the reason for that is because there's a frictional force, specifically a static friction, that is keeping the object from moving. It's good to know that the word static means not moving or stationary. The other type of friction then comes into play when you're dealing with an object that is moving. A kinetic friction is a force of friction that's generated when two substances are rubbing against each other while it's moving. Once again, this is specific for kinetic friction, or a friction that's coming from motion. Alright, so how do you calculate these types of frictions? Well, each friction is different. There's static friction and kinetic friction. This equation is more specifically for kinetic friction. When you want to calculate kinetic friction, there's two things that need to be considered. The first thing is the normal force. The normal force from the surface is going to make a difference on what your kinetic friction is. The second thing that makes a difference is something called the coefficient of friction. And that is going to have the symbol, the Greek symbol mu. Now, this symbol is unitless, it's just a number, and this depends only on the nature of the two substances. So for example, if you had cardboard rubbing against marble floor, that's going to be a different coefficient of friction than, let's say, a textbook rubbing against a marble floor, or a textbook rubbing against a tabletop. The mu depends on the two surfaces. And just so you know, the lower the mu value is, the smoother the two surfaces are. So once you know the mu and the force normal, you can then calculate your force friction. Notice here that the mu has a sub k. That just means that this is the coefficient of friction, particularly relating to kinetic friction. So let's look at an example. A cardboard carton weighing 16.5 kilograms is resting on a marble floor. If the coefficient of friction between cardboard and smooth marble is 0.20, what is the force of friction acting on the box as it's pushed along at a constant speed? The first thing I notice is that it's being pushed along at a constant speed. Not only does it tell me that I'm dealing with kinetic friction, but I'm also dealing with an object that is in equilibrium. So in other words, the sum of the forces is equal to 0. So if I think about this, if I want to solve for force friction, I need to know two things. What's the mu, and what is the force normal? Well, the mu the problem gives to me is 0.20. Now, the force normal, I need to figure that out. If I imagine the situation, I've got a floor and I've got the 16.5 kilogram block that's resting on it. Gravity is pulling the box down with 165 newtons. Since the object is in equilibrium, I know that the force normal that the tabletop pushes up, or the floor pushes up, must be equal to that. So it would be 165 newtons for the force normal. And so that's what I would plug in here, 165 newtons. Timesing 165 times 0.2 is going to give me a force of friction of 33 newtons. This concludes the video on intro to forces and types of forces.